So we're going to go over the Cartesian equation of a plane, which is very similar to the Cartesian equation of a line, except that we have an extra variable involved. So if you guys recall, when we have the scalar or the variable a in front of our x, by, cz, and d being our constant value, if we can find a normal, which is a perpendicular line to this plane, because we're specifically talking about planes, the coordinates, the x coordinate of the normal becomes the coefficient or scalar in front of x. The y value of the normal becomes the coefficient in front of y, and the z value of the normal becomes the scalar coefficient in front of the z. So if we have the normal, it can be very simple to turn into Cartesian form. We'll get into a couple of these rules a little later, but let's talk about this idea first. And there's a couple ways we can go about solving this. So let's say this is our first example here. Okay? Example 1, they've given us this normal. We know the Cartesian equation of a plane, and it's usually denoted with the Greek letter pi. So our plane is equal to ax plus by plus cz plus constant d is equal to 0. Okay? We don't always have to include our symbol in the front, but it's good to have. Why did that change from blue? There you go. So what we have here is our a value. Because we know the normal to this plane, we can replace our a with the value of -3, x. We can replace our b value with the value of +8, y. And we can replace our c value with the value of +9, which is our z. We still don't know the constant term d in this question, so we will have to go about solving that. Luckily, we know a point on this line. This point here represents an x, a y, and a z value, which means we can plug them in for the x, y, and z in this equation, which leaves us with only one variable, which we can then isolate for. So we're going to go about it that way to start. We'll have -3 multiplied by 5 plus 8 multiplied by 1 plus 9 multiplied by -6 plus d is equal to 0. We can now isolate for d. We'll have -15 plus 8 minus 54 plus d is equal to 0. We combine those, what, -7, -61? Check that to make sure. I make a lot of mistakes in my head. Okay. Which means d is the value of 61. So our Cartesian form will be -3x plus 8y plus 9z plus 61 is equal to 0. Okay? So we've taken the normal and a point and turned it into our Cartesian equation of a line. Okay? I'm just going to show you that example. There is another way we could go through this, but those ideas can be addressed in the next question. Okay? So let's go to our second example here. In our second example, they've given us a vector equation of a line that lies on this plane, and they've asked us if this point goes through. Well, I was hoping this point would be on it. I wrote the wrong question down. Changing the question a little. We're going to say that this plane contains this point. Okay? So we're going to go through this idea that we have a plane, and this lovely looking parallelogram, which I didn't draw properly, is our plane. This plane is going to contain our line here. Okay, which is denoted as vector r. And the plane is also going to contain point P in this case. Okay, so this is our point. We need to find the Cartesian equation of this plane. So there's a lot of information here. One thing we do know is on this line there is another point which is also on the plane at 2, 0, and 1. Okay? And we have point P, which is at 1, 3, and 0. In order to be able to create a plane, we're going to need two vectors. Okay? And this line here the projection vector or the direction vector, and we can find another direction vector from our point at 2, 0, 1, and P, will help us get two direction vectors for our plane. When we have two direction vectors, we can then find a normal. And once we find a normal to this plane, we'll be able to change it into Cartesian form. So the first thing we're going to do is find a direction vector from this point to point P. You want to close that door? We'll call this point A in this case, okay? So A has the coordinate of 2, 0, and 1, and P has the coordinate of 1, 3, and 0. So we want to find a direction vector for these two. We're going to subtract them. So we'll get 2 subtract 1 will give us an x value, 0 subtract 3, and 1 subtract 0. So our direction vector from A to P will be 1, negative 3, and 1. Okay? So now that we have that information, we have this direction vector from AP, and we also have the direction vector for vector R, which is negative 4, 5, and 5. Okay, so we'll call this direction vector 2 and direction vector 1. With those two direction vectors, we can find a normal. Does anyone remember how we can find a normal to two vectors?
Cross product.
Yes, cross product, okay? So we're going to find the cross product of these two vectors, and that will then give us a normal, a vector that is perpendicular to our plane. So we have our formula of A2, B3, subtract B2, A3 for an x value of the vector. A3, B1, subtract B3, A1 for the y value. And A1, B2, subtract B1, A2 for our z value. We'll denote this as our A, so A1, A2, A3. This will be our B, B1, B2, and B3. Okay? So we're going to plug our values in. Help me out as I go along. Sometimes mess this up. Negative 3 multiplied by 5, subtracted by 5 multiplied by 1 will give us our x value. A 3, 1 multiplied by negative 4, subtract B3, which is 5, multiplied by 1. And finally, our A1 is 1 multiplied by B2, which is 5, minus B1, negative 4, multiplied by A2, which is negative 3. So I've underlined them. They should all be underlined twice. Yeah, so I think I've done this correctly. Whoa, that's a little much. We'll go from here. We have negative 15 minus 5, negative 4 minus 5, and 5 minus 12, which will give us negative 20, negative 9, and negative 7. So this is now a normal to the plane we were on before. Because of that normal, we know we can substitute that in for the Cartesian equation as A, B, and C. So what we'll do from there is we'll have negative 20x minus 9y minus 7z plus d is equal to the value of 0. We'll still have to find a value of d, in which case we need a point on this plane. We know that point P is on the plane 1, 3, 0. So we'll use point P at 1, 3, and 0 and plug it in for the x, y, and z values, then isolate for d. So negative 20 multiplied by 1 minus 9 multiplied by 3 minus 7 multiplied by 0 plus d will give us 0. Negative 20 minus 27 plus d equals 0. I think d will be positive 47, which means our Cartesian form is negative 20x minus 9y minus 7z plus 47 is equal to 0. Whole lot of info.